Okay, sorry. So in the conservation of energy video, 6.4 or whatever it is, we talked about the roller coaster. So let's look at something similar to a roller coaster, namely a skate park. You guys agree that's basically the same as a roller coaster? Right? Okay, so let's think about what forces are acting on our dude here, okay? So gravity's pulling my guy down, right? Is it going to let me write? Oh, it is, very good. Gravity's going to pull the guy down, right? I've got it set so it's frictionless, so we don't need to worry about friction. There's only one other force, which is normal force. Now, so law of conservation of energy says if your non-conservative forces don't do work, then your total energy is constant. So there's only two forces. Gravity, we don't need to worry about that because it's a conservative force, right? Okay. Normal force, that's non-conservative, right? Remember, the only two conservative forces are gravity or a spring. Okay? So anything else is non-conservative. Tell me something important about the direction that normal force is pointing in, you guys. Perpendicular to the direction of motion, right? So the work done by my normal force is going to be 0. So that means that in this problem, my total energy should be conserved. Okay? So, in this problem, what type of energy does my dude have right now?
Potential.
Gravitational potential energy, right? Look, all of his energy is gravitational potential energy, right? Now look, normal force doesn't do work on him. Gravity is going to do work on him though, right? Because it's not perpendicular to motion. Okay, so what's going to happen as he goes down the hill? What's going to happen? Just in simple words. I'm a third grader. What's going to happen? Simple words.
He's going to speed up.
He's going to speed up. So talk to me about energy. If he's speeding up, talk to me about energy.
It means that his potential energy is
Kinetic energy is gaining.
There you go. Good. If he's speeding up, he's gaining kinetic energy, right? So he's gaining kinetic energy. That feels like his energy is changing. But what other kind of energy is changing? Potential energy, right? As he goes down the hill, his potential energy is decreasing, right? Because he's losing height. Okay, so watch. Well, here, we'll turn off slow motion. Oh. Here we go. Okay, so look at the little graph here. So right now his KE is increasing. Here, make it on slow motion. So as he goes down the hill, he loses potential energy and gains kinetic. As he goes up the hill, he gains potential but loses kinetic. But the total is always the same, right? It's just, right? Okay, so your total energy is the same. All you're doing is you're converting GPE to KE and then KE to GPE, but the total stays the same. Okay? And I think I said that mathematically, but I did not show you this in the video, and I meant to insert this little video clip into there, and I forgot to do it. Yes, sir?
Oh, so like what happens when kinetic potential energy are equal to one another?
Nothing. Just that. So there is a point when he's partway down when... I missed it. So pretend these are equal. So at this point, the idea is half of his total energy is potential, half of his total energy is kinetic. So it turns out that if, assuming you start at rest and end at rest, no, start at rest and end at a height of 0, that'll happen at the halfway point, like halfway height-wise. Okay, yeah?
So just for chuckles, can I turn friction on?
Let's see, does it let
It's
us?
on the bottom.
Why am I blind?
It's in a dark square at the bottom.
Oh, gotcha. Right, thanks. Yeah. All right, so what do you think is going to happen, you guys?
Some of the energy is going to turn into thermal energy.
Yeah, so let's turn on our graph. So the idea is, here, let's increase his mass a little so we can... All right, so yeah, so what's going to happen is as he goes down the hill, there's going to be friction between the wheels and the car, right? You've done this before. When you rub your hands together, what do?
And hot.
They get hot, right? So we're going to see a decrease in kinetic and potential energy total, but the thermal will go up. I don't know why it's so much more at the bottom. Maybe it's just because he's moving faster, so there's...
Yeah.
Yeah. Not very exciting, right? Okay, cool, you guys?
So that's exciting.
Okay. All right. So I guess the last thing I'll say is this. In terms of problem solving, every single one of these problems is the same. You identify the important points in the object's motion. All right? Every single problem will be set up like this. You're going to be given one point, and at that point, you're going to know the height, you're going to know the velocity. Smiley face means you know it. It's an internationally recognized symbol. Okay? So we know the height, we know the velocity. I learned that. I'm sure your physics professor in college will do the same thing. All right? So we know the height. Oh, I can use my height to find my GPE, because it's mass times acceleration of gravity times height. Oh, I know the velocity. I can find my kinetic energy. It's 1/2 mv squared. Oh, I can find my total energy, right? Just by adding those two things together. Cool? And then the way the problems will be set up is it'll say, all right, that's that. Now, at some later point, we know the height. I said, we know the height, find the velocity, or vice versa. Okay? And so all you're going to do is you're going to write an expression for the total energy at this point, you're going to write an expression for the total energy at this point, and you're going to set them equal to each other. All right? So basically your equation boils down to this. You're going to have mass times acceleration of gravity times the height at point A plus 1/2 mass times the velocity at A squared equals mass times acceleration of gravity times height at B plus 1/2 mass times the velocity at B squared. And there's 4 variables here. Well, not counting mass. There's 2 heights, 2 velocities. You'll always be given 3 of the 4. You solve for the missing one. Okay? So, but to do this, you have to think about the 2 important points. Okay? You cannot solve these problems by just looking at one point. Andrew.
So when it's like, how fast is it moving when it's halfway down? Would you just make, well, the height obviously would be,
Half of your total.
and then, but you don't know the mass, then you don't know the velocity. How would you?
So the mass ends up not mattering. I did an example like this in the video. Do you guys remember why does it? Look at this equation here. Yeah, do you see how all of these have m in them?
Yes.
So you can go through and just divide both sides of the equation by m, and then mass, 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 and mass all cancel. Cool?
Yeah.
So the only time I'll give you the mass is if it doesn't cancel. So the times when it won't cancel is if there's elastic potential energy is another form of energy, because that doesn't depend on it. And then later on when we get to work, when we get to the total energy changing, the mass will matter.
Right.
Follow?
Yeah.
Good questions. AJ,
I don't understand how they cancel out.
if I give you this equation, I don't know why I would ever do this, but 3x minus 4x equals, I don't know, 6x y plus 3x. Do you agree you can factor an x out of all of those? All right, so this becomes x times 3 minus 4. And this becomes x times 6y plus 3, right? So divide both sides by x. Follow? So then you have 3 minus 4 equals this other mass, and you can solve it. Same exact thing. Cool, you guys? Questions? Okay, so I'm going to shut up. If you would like to work through a problem in more detail, like if you want to see one worked all the way out, would anybody like that? Okay, if you're, what's that?
Can we do like one on 6.4a?
Why don't you, I think I'd rather do a separate one because I think the practice is good for you. Sorry. I'm happy to do a different one if you want. Okay. All right, but if you want one, holler at me and I'm happy to sit down with you. And if a few people say it, then we'll grab a lab table and do that. Okay? There you go. So.